Okay, let's unpack this. Imagine needing to measure electricity with, well, almost unimaginable precision. The kind of precision you'd need to build, say, future quantum computers or cutting-edge communication tech. I mean, how would you even start to get measurements that perfect? Tie them back to basic physics.
Yeah, that's the core challenge, isn't it? For a long time, our standards, like the volt, were actually based on physical objects, artifacts.
Like what?
Things like carefully made electrochemical cell batteries, basically. But they have limits, They
Yeah.
drift, they change with temperature, humidity,
Right.
and comparing them between different labs always meant losing a bit of accuracy. So for the really advanced tech, you need something, well, fundamentally better, something inherently perfect based on nature itself.
And that is exactly what we're diving into today. We're exploring the really fascinating world of superconductive electronics at NIST,
That's the National Institute of Standards and Technology.
right? Specifically their labs out in Boulder, Colorado.
And our guide for this is a presentation by Dr. Sam Benz. He leads the Superconductive Electronics Group there. He's been doing this for, over 30 years? Really pioneering work.
Yeah, incredible dedication. So our mission here is to kind of translate this really technical stuff, quantum-based signal synthesis and measurements, they call it, into something that makes sense for, well, pretty much anyone. Maybe you're just curious or a student thinking about science or engineering, or maybe you've got a meeting coming up on something related. We want to break it down.
And this is where it gets really interesting, I think. We'll look at how they use the really weird properties of superconductors.
Just super cold stuff.
Exactly. To create electrical standards that aren't just accurate, they're, you could say, quantum perfect. And we'll see how that connects to everything from calibrating everyday electronics, maybe even the phone in your pocket eventually, to actually controlling the bits in a future quantum computer.
Okay, so let's start at the beginning. NIST. What exactly is NIST?
Well, think of them as the nation's measurement lab. They used to be called the Bureau of Standards, way back.
Right.
Their job is basically to make sure measurements are consistent and accurate across the U.S., which helps industry, commerce, science, everything. But it's much broader now. They do a ton of cutting-edge research and tech development to push those measurement limits, kind of the scientific backbone for innovation.
And the Boulder Lab's been doing this kind of thing for a while.
Oh, yeah, a long history. Some of the buildings go back to the 50s. President Eisenhower actually dedicated some of them. But they also have brand new facilities, state-of-the-art clean rooms. That's where they make these incredibly tiny devices we're going to talk about. It's a real mix.
Okay, so NIST equals super precise measurements and enabling tech. Now, the key thing, superconductors. Why use these materials that you have to cool down like crazy?
Okay. That's the magic ingredient. Superconductors are special materials that when you cool them way, way down,
How cold are we talking?
like 4 Kelvin, that's just 4 degrees above absolute zero, minus 452 Fahrenheit, roughly, usually using liquid helium.
Right.
At that temperature, something amazing happens. Their electrical resistance completely disappears. Zero.
So electricity just flows
Yeah.
forever without losing energy.
Pretty much, like frictionless flow for electrons. That's super useful for signals, especially high-frequency ones, because they don't get weaker. But there's another key thing, quantum mechanics.
Uh-oh.
Haha, yeah. In a superconductor, electrons pair up and act together, like a single quantum wave. It's this collective quantum behavior that NIST leverages to make these perfect standards. It's ideal for tackling big challenges like energy-efficient computing or quantum information tech.
Got it. Super cold, zero resistance in quantum waves.
Okay.
And Dr. Benz's group, they focus on something called a Josephson junction. What on earth is that?
Right. The Josephson junction is the heart of it all. It's basically a weak link between two pieces of superconductor.
A weak link. That sounds fragile.
It is weak, but that's where the quantum magic happens. Imagine you have superconductor, then a very thin barrier, maybe an insulator, maybe a normal metal, and then superconductor again.
Well, yeah.
That collective electron wave we talked about, it can actually tunnel or sort of proximity couple right across that weak barrier.
Wave just phases through.
Kind of like that, yeah.
Huh.
Now, here's the really mind-bending part. If you apply a voltage across that junction, the relationship, the phase difference between the quantum waves on either side changes in a very specific repeating way. And each time it goes through a full cycle, technically a 2π cycle, the junction spits out a tiny pulse of voltage.
A voltage pulse.
Yes, but not just any pulse. These are quantized pulses.
Untized meaning.
Meaning each pulse is fundamentally identical in a very specific way. The total voltage multiplied by the time duration of that pulse, what physicists call the area under the pulse, is exactly fixed. It's determined by fundamental constants of nature. Planck's constant H divided by twice the electron charge, 2e.
H divided by 2e. So every single pulse has this exact same fundamental value baked in by the laws of physics.
Precisely. And crucially, there's no other electronic device we know of that inherently generates pulses like this with this perfectly quantized property. That direct link to H2E is why they're invaluable for making standards based on physics itself, not just on some physical object we calibrated.
That is genuinely amazing. Using this deep physics to build a ruler for electricity. So how do they go from these tiny, perfect pulses to something useful, like defining a volt?
Right, because one junction doesn't do much on its own. The voltage step it produces is tiny.
Pretty tiny.
Well, that H2E constant means you get about 2 microvolts, 2 millionths of a volt for every gigahertz of frequency you drive the junction with.
Okay.
So if you use a standard microwave signal, say 10 gigahertz, one junction gives you maybe 20 microvolts. To get to voltages people actually use in labs or industry like 1 volt or 10 volts,
You need a lot more.
you need a huge number of them connected in series. We're talking hundreds of thousands, maybe 500,000 junctions for a 10-volt standard.
Wow. 500,000 tiny junctions all working together. That sounds hard.
Oh, it is. That's the monumental engineering challenge they solved over decades, making hundreds of thousands of these microscopic junctions almost perfectly identical.
Why identical?
Because each junction only produces that perfect quantum voltage step over a specific range of operating conditions. The input current, the microwave power. They call this the quantum locking range.
The quantum locking range. The sweet spot.
Exactly. It's the range where the junction is locked onto that perfect quantum behavior defined by F times H2E times an integer n. For the whole array of 500,000 junctions to act as one stable voltage source, all their individual locking ranges need to overlap.
Okay, I see.
And you also have to get the microwave power distributed perfectly evenly to all of them across the whole chip. The fabrication and the system design are incredibly sophisticated.
So let's talk applications. The DC voltage standard first. How does that work?
Right, that's the Programmable Josephson Voltage Standard, or PJVS. They drive this massive series array with a super precise microwave frequency.
And that generates incredibly stable, constant DC voltage outputs. The voltage is just perfectly set by that frequency, H2E, and which step-in they choose. As long as it's operating in that locking range, the voltage is fundamentally accurate.
And programmable means?
It means they don't just get one voltage, they actually divide the huge array into smaller segments.
Okay.
And they can digitally turn these segments on or off, or bias them to produce positive voltage, negative voltage, or zero voltage. By combining these segments, they can synthesize or program almost any precise DC voltage value they need, positive or negative, within the system's total range. It's incredibly flexible.
That's amazing for DC. Steady voltage. But what about AC signals, like a perfect sine wave? That seems way trickier.
It is trickier, but they use the same core idea. That's the Josephson Arbitrary Waveform Synthesizer, or JAWS system.
Okay.
Here, they use those same quantized voltage pulses, but they time their generation very, very precisely.
Timing the pulses, how does that make AC? Think of it like super fast digital to analog conversion. They rapidly switch different parts of the array on and off, generating streams of positive and negative quantized pulses. By controlling the timing and density of these pulses very carefully,
They build up the AC wave shape.
exactly, they can synthesize incredibly pure AC waveforms, like a perfect sine wave or triangles or ramps or really any arbitrary shape they want. And because each pulse is fundamentally quantized,
The whole waveform is fundamentally accurate.
precisely, things like the RMS voltage, the effective power of the AC signal, can be calculated directly from the pulse pattern in H2E. No need for separate calibration. It's synthesized perfectly from the start.
This quantum approach, it sounds like a massive improvement. What did it replace? What were voltage standards like before this?
Yeah, it was a huge leap. Before quantum standards, we relied on artifact standards. For DC voltage, the main thing was the Weston cell.
You mentioned that, a kind of fancy battery.
Essentially, yes. A glass electrochemical cell, very carefully made with specific chemicals like cadmium and mercury, designed to produce a stable voltage around 1.018 volts.
Okay.
National labs around the world would maintain banks of these cells. But, like we said, they weren't perfect. They aged, they were sensitive to temperature changes, even barometric pressure or vibration.
And comparing them was tricky.
Very. To ensure voltages were consistent internationally, Labs had to physically ship their best Weston cells to a central lab, like the International Bureau of Weights and Measures in France, for comparison. Each shipment, each comparison introduced small errors. You lost accuracy down the chain.
So the world's definition of a volt depended on these physical objects that could change.
That's right. Compare that to the Josephson standard. It's based on H2E and frequency. Those are the same everywhere, yesterday, today, tomorrow. As long as your device is working correctly in its locking range, you have the standard voltage. It revolutionized measurement agreement worldwide.
And you mentioned this played a role in like the biggest change in measurement science recently. Well, redefining the SI units.
Absolutely fundamental to it. This work on quantum electrical standards, the Josephson effect for voltage, and a related quantum effect, the quantum Hall effect for resistance, was critical for the redefinition of the International System of Units, the SI, in 2018.
That's when they redefined the kilogram, right?
Yeah.
Got rid of the metal block in Paris.
Exactly.
Right.
For over a century, the kilogram was literally defined by that one platinum-iridium cylinder. But in 2018, all the base SI units were redefined based on fundamental constants of nature. The kilogram is now defined by setting Planck's constant H to an exact numerical value. And the way they linked mass to Planck's constant was using a device called a Kibble balance.
A Kibble balance.
It's an incredibly precise machine that essentially balances mass against electromagnetic force. To make that link to Planck's constant, you need to measure electrical power voltage times current with extraordinary accuracy. And NIST's Josephson voltage standard and quantum Hall resistance standard provided exactly that quantum-based electrical measurement needed to make the Kibble balance work and redefine the kilogram.
Wow. So these superconducting circuits were directly involved in changing how we define mass itself.
Directly. It's a beautiful example of how progress in one area of fundamental measurement enables breakthroughs in others. It connects everything together.
Okay, so the impact is huge. But the work isn't stopping at DC and audio frequencies, is it? You mentioned they're pushing into radio frequency.
Yes, absolutely. A big effort now is developing RF JAWS radio frequency synthesizers. The goal is to generate those perfect arbitrary waveforms, but at much higher frequencies, into the megahertz and gigahertz range.
Why is that important?
Think about all our modern wireless tech. Cell phones, Wi-Fi, radar, satellite communications. They all operate at these high frequencies. Calibrating the test equipment for those devices accurately is crucial.
And it's harder at RF.
It is. RF circuits usually need to be matched to a specific impedance, typically 50 ohms. That's like ensuring the electrical highway has the right properties for the signal. Making the superconducting chip interact correctly with this 50 ohm environment while still generating those perfect quantum signals is a real challenge, but they're making progress. Dr. Benz mentioned operation up to 3 gigahertz already.
So creating physics-perfect signals to calibrate our wireless world. What else? You mentioned pulse generators.
Right, Josephson pulse generators, or JPJs. This is again about using those inherently quantized pulses, H2E, but focusing on generating streams of them with incredibly precise timing.
And the application for that is?
A key area is control signals for quantum computing. Many types of quantum bits, or qubits, especially superconducting ones, are controlled using precisely timed microwave pulses. Using a JPJ allows you to generate those control pulses with quantum-level precision in their timing and shape. Dr. Benz showed an example where these quantized pulses could accurately rotate the state of a superconducting qubit. So you're using quantum electrical signals to control quantum information.
Using quantum to control quantum. Makes sense. And there was one more new thing. A sampler.
Yes, the Josephson sampler. This is pretty new, started around 2022. The idea here isn't generating signals, but measuring them. Specifically measuring very fast signals right down at the cryogenic temperatures where these superconducting circuits operate.
Like a super fast camera for electricity in the cold.
Exactly like that. It uses Josephson junctions as incredibly fast switches and comparators to take tiny snapshots or samples of a rapidly changing voltage waveform. This is vital for understanding, debugging, and improving high-speed superconducting circuits, including things like superconducting logic.
Superconducting logic. Like super fast computer chips.
Potentially, yes. It's called SFQ logic, single flux quantum. It uses even tinier, faster quantum pulses. Being able to measure those pulses is key, and the sampler is already showing amazing results. They've measured pulses as short as 3 picoseconds.
3 picoseconds? That's a trillionth of a second. That's just hard to get your head around.
It's incredibly fast. Being able to see signals change on that time scale, right where the action is happening in the cryostat, is a huge capability for developing next-generation electronics.
So all this amazing lab work, how does it actually get out to the world? Do companies use this stuff?
Yes, absolutely. NIST doesn't just do the research. They package this technology into usable systems. They call them standard reference instruments.
Okay.
These are complete systems, the chip, the cryogenics to keep it cold, the electronics to drive it, the software to control it all bundled up so that other metrology labs, universities, and high-tech companies can actually buy and use them for their own calibrations.
So they make it user-friendly. You don't need to be a NIST physicist.
That's the goal. It took decades, not just to figure out the physics and build the chips, but to engineer the whole system to be robust, reliable, and relatively easy to operate. Dr. Benz emphasized the team effort involved people fabricating chips in the clean room, testing them in those big liquid helium dewars.
Those thermos things.
Yeah, basically giant thermoses, or even colder in dilution refrigerators for quantum experiments. Then calibrating instruments, writing software. It's a whole pipeline from fundamental science to a practical tool.
And this expertise helps in other areas too, right? Not just voltage.
Definitely. Their deep knowledge of superconductors, Josephson junctions, and working at ultra-low temperatures feeds into other projects. Things like developing ultra-sensitive detectors for astronomy, trying to see the faintest signals from the early universe, or for analyzing materials. They use related tech like SCEDs, superconducting quantum interference devices, incredibly sensitive magnetic field detectors, or transition edge sensors, which are like super sensitive thermometers. And they also contribute to research on high-speed computing using superconducting logic.
So it's really a hub of expertise for all things superconducting and cryogenic.
That's a good way to put it, leveraging these unique quantum phenomena.
Well, we've covered a lot of ground today. We went from this sort of weird quantum effect in a weak link between superconductors, the Josephson junction, all the way to how it's now defining global electrical standards, helping redefine the kilogram, and even potentially controlling the bits in quantum computers.
It's really quite a story, isn't it? How understanding and then engineering something so fundamental like that quantized pulse area H2E leads to technologies that underpin so much accuracy in our world and open up entirely new possibilities.
It really is. And it makes you wonder, doesn't it, as our technology gets more and more entangled with the quantum world, how will these ultra-precise quantum-based standards keep evolving? What else might they enable down the road, things we maybe can't even guess at yet?
That's the exciting part about foundational measurement science, you know? You build a better ruler, and people inevitably find new and amazing things to measure and build with it. It's a continuous cycle of innovation.
Definitely something to ponder. Well, thanks for walking us through that. Really fascinating stuff.
My pleasure. It's an amazing field.
And something for all of you to think about until our next deep dive.